So the class today, we're going to start talking about a new topic, which is the concept of NoSQL. We're going to talk about some of the guarantees that we can have in such systems, as well as two of the more basic forms of NoSQL database that we can find in practice. So we'll have in general, we'll have 3 lectures on NoSQL. The overall idea is that we've spoken about processing structured and unstructured data in a distributed setting using MapReduce, Pig, and Spark, and Hadoop, and so forth. We've also spoken about storing and indexing unstructured information in terms of text. So using Elasticsearch and Lucene to be able to provide indexes over text documents. The last main topic we haven't really described is storing structured information in a scalable way over massive data sets. So this is the topic that we're going to finish with. And after this, you'll have seen how to process data, how to store and index text, and how to store and index structured data at large scale. So in terms of storing structured information, structured data, in a big data setting or where we have lots of data. Well, if we think about storing structured data in general, we probably will automatically think of relational databases as being the traditional standard way to index structured data. So it's this sort of traditional way of you have these very clean tables and you can nicely categorize all of your data within your tables, and everything is very neat and efficient in terms of search. So relational databases, of course, are very widely used and are very effective, very efficient in terms of implementation. But some of the new sorts of use cases that we've seen, particularly with the web, they don't really require relational databases. They could use relational databases, but often the types of data and the volumes of data that they have to deal with, it might not make sense to use relational databases in all such cases. So there were some new requirements, novel requirements that were starting to emerge with these, especially with these web companies that were having to deal with massive amounts of diverse data. So for this reason, the database landscape has diversified a bit away from just relational databases. So this idea that you can just take a relational database like Postgres or Oracle or whatever it might be, and that will serve whatever data management needs you have. This is an idea that was around for a while, but has now really disappeared. So we have more specialized databases for different types of scenarios. So there was a paper, an influential paper, written by 2 authors. Michael Stonebraker, won the Turing Award, the sort of Nobel of computer science a few years ago. And essentially, it's arguing that this idea that you just use a relational database and you're done, this idea has come and gone, right? So this is no longer valid nowadays. So why do they say this specifically? Well, if we think about a relational database, what we will assume is that every relational database implementation, or 99% of them, maybe there's some exception, but they implement the SQL standard. So they allow for querying and for inserting and modifying tables using the structured query language standard, which you would have seen before in a database course. This is a very useful language and it's extremely popular in practice. It's a declarative language, so you can specify what you're looking for and not necessarily how it should be evaluated. That would be up to the relational database system to decide in what order to do joins, which pattern to begin with, what kinds of join algorithms to apply. When you write a query, you don't worry about that. You just say what you want. The language is also expressive in the sense that you can express relatively complex queries in SQL. So the core of the language is very expressive, and there are lots of features for doing aggregations, for ordering, and so forth. The downside of SQL is that it's difficult to optimize because it's such a general language in which you can do so many things. it can be difficult to optimize the evaluation of queries in that language. It is also difficult to distribute. There's no obvious way in which you might go about distributing different tables or evaluating queries in a distributed setting. So it's thinking about it, you can come up with some solutions. It's not, I don't want to say that it's impossible to optimize or to distribute. It is possible to do both of these, but there's definitely some overheads involved in terms of handling the full language in a good way. The other thing we associate with relational databases that you might remember are these ACID guarantees to do with transactions. So in terms of the benefits, strengths and benefits, guarantees correct behavior and allows for supporting transactions. So we have atomicity, consistency, isolation, and durability. Okay, so atomicity means that a transaction is applied as if it were one operation, or otherwise it either runs entirely or fails entirely. Consistency means that each transaction is guaranteed to maintain the consistency of the database. If it doesn't, it will just fail entirely. Isolation has to do with the idea that two transactions in parallel cannot affect each other in an undesirable way, that somehow the results will be equivalent to running one transaction and then the other. And durability refers to the fact that once a transaction has been completed and acknowledged, that the database will reflect those changes. It will remember the changes in the transaction. So these guarantees are very important for guaranteeing correct behavior. For example, in the context of a bank, if we have lots of transactional data, we don't want to forget some transactions that were made by our clients. On the negative side, implementing ACID is costly and it's difficult to distribute these guarantees. So it's not trivial to somehow provide ACID in a distributed setting. And we'll talk more about what sorts of guarantees we can or cannot have in a distributed setting. So we have some positives, some negatives for SQL and ACID. In terms of the costs of ACID, in terms of the costs of transactions, this was another paper, which in this case by some leading people in the database community, who were looking at the costs overall of managing, of providing ACID through transaction support. And what they found is that in this was a particular case, which was a particular database that they looked at, which was actually an in-memory database. Which is kind of important. But in this case, what they found is that 6.8% of the time of the steps or instructions executed by the database involved useful work, involved actually doing what the command had said, involved the insert, involved the getting the results for the query. A lot of the time, a lot of the overhead was dedicated to things that were related to transactions. So buffering, latching, locking, logging, so logging is important to ensure durability, for example. Locking is important for isolation to make sure you don't have two transactions reading and writing in an unpredictable way to the same data. So these were all somehow, related to, we can see that essentially there's a large overhead for ACID. So in terms of the consequence of this, it would be possible in this database to do 640 transactions per second in terms of transactional support. And it would be possible to do 12,700 transactions per second for systems without any transactional support. So essentially we can see that we can do something like almost 20 times more transactions per second. What is latching? I'm actually not too sure. I think latching might be related to locking in terms of somehow. So buffer manager is just related to disk I/O. So it's like being able to buffer certain blocks into disk and knowing which ones you might want to read next and reading ahead and so forth. Locking, logging, and hand-coded optimizations are probably something specific to the database. Latching, I think, I'm not sure. I'd have to see. I think it might be related somehow to queuing up requests. I'm not really too sure. I'll have to find out. So in any case, the main costs here overall would be the 93.2% of the operations, the time is spent in terms of transactional support. So this is rather costly. So one of the aspects here to take into account is, okay, it has this large cost, but do we always really need ACID? Are we sure that we always really need this sort of transactional support? Maybe there are some alternatives to relational databases then for big data that move aside from the traditional kind of support for SQL and ACID. So has anyone heard of NoSQL? I'm sure many of you have heard of NoSQL, right? So what does NoSQL mean? So yeah, I'm sure some. So if you haven't used it, well, if you've used Elasticsearch, if you did the last lab, then you would know. So NoSQL doesn't mean no SQL, right? So what it means actually more strictly is not only SQL. It's just this idea of it's the counter to this idea of one size fits all, that if you need a database, you get a relational database and that's it. You use that. So yeah, so not only SQL. Yeah. So no more SQL either. So but the world still needs SQL, but it also needs sometimes other things, I would say. So SQL is still very popular. So in terms of the popularity overall, we can look at this, database engine ranking that we've referred to maybe once or twice before, which looks at the popularity of different database management systems. In terms of, number of searches, number of questions in Stack Overflow, number of tweets about them, these sorts of measures. So not very scientific, but a nice way maybe to get an estimate of their popularity. And we see that the first four, Oracle, MySQL, Microsoft SQL Server, and Postgres, are still the most popular database management systems, which is to say that they are still, the market is somehow still dominated, or in practice, most databases in use are still relational databases. But we see some new ones. We see, for example, MongoDB, which is not relational, it's a document. Okay, we see another relational database. Then we see a key value store. We see Elasticsearch, which is a search engine. We see a few more relational databases. We have a wide column store. We have a search engine. We have a graph system here. And we have some multi-model databases. Essentially, multi-model is just this idea that they can also store like JSON documents, or they can store different types of formats, which is becoming more and more common. So all of these non-relational databases here, these are all essentially NoSQL systems. So we have document, key value, search engine, which is kind of the same as document, wide column, which is kind of a tabular format, graph databases, and so forth. So these are just different types of search engine, database database management systems, not relational database management systems. So different types of databases. Okay, so when we think of NoSQL, there's this inherent trade-off between having lots of features and the scale and performance of the system that the system can guarantee. So for example, a common trade-off would be to say, we don't provide SQL support anymore. The language is too complex. Rather, we provide a much simpler query language that people can use. And if people, based on this query language, we can guarantee that any query we can run in efficiently. We can run it as a direct lookup. We can run it under a second, or whatever it might be. Another trade-off would be to say, we don't need ACID anymore. So essentially, we're going to remove all of the overhead of supporting transactional systems. So we'll talk more about these features and scale and performance, and different types of NoSQL system have different kind of answers to this trade-off. So there's a diverse selection of NoSQL systems that have different ways of seeing this trade-off. But some common characteristics of NoSQL systems: they are often distributed to deal with large-scale data. They're often simpler. They often support simpler languages than SQL. So much more low level. For example, they might not allow for doing aggregations, or they might not allow joins, and so forth. There are different flavors for different scenarios. So unlike relational database management systems that tend to be more or less the same, like, whatever you do in MariaDB or MySQL, you could also do in Postgres and vice versa, more or less. And this is not the case here for NoSQL. And each of the different types of flavor of NoSQL is kind of targeting a different type of application. So the four main flavors that we see are key value stores. These are the simplest. So they're by far the simplest. They're effectively like a dictionary, a map. They're just, given a key, get a value. And these are the most scalable, but they're also the simplest. So all they allow you to do is sort of have like a map, put, get, remove type interface. Next, we have column families, which are the next in terms of complexity. But there is a cost in terms of scale, a slight cost, I would say, but they're slightly more flexible, or slightly, you can do more things with them. So the column families, they're also called tabular stores, or wide table stores. There's quite a few names for them, but essentially they're like tables, but where it's very similar to key value stores, but where the values are indexed like tuples. So it means that rather than having, a simple value, you can have a value that has multiple columns, right? So the key then is essentially like the primary key of the table. So you could consider these as indexing tables in a way. Document databases. This refers to NoSQL systems that would index, for example, JSON documents or text documents or XML documents, these sorts of text or semi-structured formats. We've already seen one of those, which was Elasticsearch, which is one of the most popular, the second most popular document database. And then we have graph databases, which are for querying data that are naturally structured as graphs, and allows also to do, for example, navigational queries, which allow us to find paths in graphs. For example, maybe we have a graph that's indicating a transport network, and we can find, routes from one metro station to another metro station, these sorts of queries. So we have different types that are, that are different from SQL. They're not supporting SQL. They have their own languages. They have their own ways of indexing and so forth. And each one is kind of targeting different types of use cases. The simplest being key value stores that we have here. Where would SQL DB be in that graph in terms of complexity and size? It's a very good question. I would say relational databases and graph databases, in terms of the types of query languages that graph databases support, are very similar in terms of what should be possible for size and complexity. Graph databases might even be slightly more complex in that they have certain types of queries you couldn't do in SQL. So, but it would be somewhere around here, right? So in general, I would say as well that the complexity here, this is not really a linear thing. These two families here, I would say, are much simpler and much more scalable than these two flavors here. But it depends on so many factors, and every system is different. That I would say really these systems should be much more scalable and much less complex. Document databases, they're very different, so it's hard to characterize them generally. And graph databases would have maybe a similar complexity to relational databases. So I would say here, around here for relational databases. Any other questions or doubts? Okay. So we'll talk in more detail. Actually, this would be kind of, a main part of the next 3 classes will be looking in detail at, the details of what these flavors are and some examples of the most common databases for that. But first, before we kind of jump into specific NoSQL systems, it would be good to talk a little bit more about the limitations of distributed databases. So there is this general notion called the Cap Theorem, And the Cap theorem is something like an equivalent to ACID, but for distributed databases or distributed computing in general, I guess. So we'll talk a little bit about the Cap theorem. And much like ACID, it speaks about the sorts of guarantees that we can have when querying distributed databases or doing distributed computing. So what is Cap? It refers to three guarantees that a distributed system could make. So the first one is consistency, which states that all nodes must have a consistent view of the system. This is a little bit different to consistency in the case of ACID, which is actually more about satisfying the integrity constraints of the relational database, like make sure you don't break any key constraints, make sure you know the foreign keys correspond, and whatever other constraints you have. Here, there's no notion of such a thing. It's just that somehow if whatever node, which is like a machine in the distributed system, asks for a value, they would get the same value. They agree on the values, the state of the data. Availability refers to this idea that every read or write can be acted upon. So essentially, it's the system remains operating all of the time, receiving reads and writes. And a third guarantee is partition tolerance, which refers to the idea that a system works even if messages are lost. So this means, for example, if we have 10 machines and all of a sudden, maybe on 2 different racks, and now the racks can't communicate to each other, for example, that the system can still continue to operate, even if messages are lost between the different machines of the distributed system. So these are 3 hypothetical guarantees that we could consider in a distributed system. And then, okay, so just to note here as well, the A is different to ACID. It doesn't correspond at all. It's atomicity in ACID and availability in Cap. And the C, although both are called consistency, they're really quite different notions of consistency. So this is kind of very different to ACID. It's at a kind of different level. So we're talking about distributed systems. So in general, what we'll imagine, just for an example, I mean, it refers to all sorts of different scenarios, but we're going to imagine a distributed system where we have information about users and we have 2 replicas of the data. So this machine here indexes all of the data for users A to E, F to J, K to S, and T to Z. And here it's the same, but we're just creating a copy of the data. Okay, so we have a replication factor of 2. We have some sort of abstract database or whatever it is, storage system that is storing the data about these users. So in terms of consistency, it means that, okay, if this machine here thinks that there's 891 users in M, right, whose username starts with M, for example, then all of the other machines, if they were to ask for the same value within the distributed system, if they were to look it up, they would have a same view, they would get the same answer. Okay, so they somehow agree on the values within the system. Availability means that if there is, as a distributed system, as a whole, that the distributed system should respond to any requests. So they might be queries. For example, maybe a client here is asking how many users start with M. Then the distributed system must provide a response, must somehow respond to the query. Partition tolerance, it means that if there is a partition in the system, then the system continues to work well. So in this case, if there is a request, then the system will continue to return a response. So partition tolerance is sort of in the context of consistency and availability. I think it's sort of related. You can't really talk about partition tolerance without talking about some other guarantees. So it continues to provide the other guarantees if there is a partition of consistency and availability, or whatever other guarantees you wish to invoke. So essentially, it's this idea that the system continues to work well whenever there is a partition. So can a distributed system guarantee consistency, availability, and partition tolerance at the same time? This is sort of the question behind CAP. And the answer is, what do you think? Yes or no? So it seems like it's kind of a hopeless case. So in this case, it's no. So the answer is no. Nope. So why is that? Yeah, you have to choose two. Yeah. So this kind of came around because, there were papers that were claiming to, with systems that were kind of claiming more or less to do all three of these and to have all these guarantees and so forth. But in a very simple sense, it's not possible. It's just to say you can't do this, right? So you can't have consistency, availability, and partition tolerance at the same time. So as a kind of a sketch of a proof you could do, I mean, it's relatively straightforward. Let's say initially that we have this view in the distributed system. We initially have a consistent state. So all of the machines see that there's 891 users in M. Now, so there's a consistent agreement on that value. Now there's a partition. Okay, so what does this partition mean? It means that these nodes can't communicate with these nodes here. Maybe, this could be for various reasons. Maybe these were on different racks. Maybe, these machines here are on one rack and these machines here were on another rack. And now there's a problem communicating between these racks or whatever it might be. Maybe it's just that the system is overloaded and there's so many messages that they can't be processed. There's a variety of different reasons why this might happen. Maybe a mouse chewed through a cable connecting the different racks. But so we have this partition, and now Madonna enters our system, and now this part of the partition, this part of the distributed system, sees that, okay, now there's 892 users in M. This, even though there is a partition, they cannot reject the request because of availability. So in terms of availability, the distributed system has to be up, has to be able to respond to the request. So how many users start with them? So now a client asks, there is some element, some client asks here in this part of the system, how many users start with them? This has to be responded. And in this case, they could give the incorrect answer because they still haven't seen this Madonna update here. So already with the Madonna update on one part of the partition, the other, there's no way a consistent state can be achieved. Right? And we can see that, if we ask here how many users start with them, then they will give us the old response. So, okay, it's maybe intuitive enough, right? There's no way we can continue functioning perfectly if there's a partition in the system such that, the different parts of the distributed system cannot communicate. So the main message behind all of this, the main takeaway is that you have to choose two of these things. So you have to choose either CA, AP, or CP. So another way to say it is that, you can have C systems, A systems, P systems, CP systems, CA systems, AP systems, but you can never have a CAP system. So you have to choose two. There's no intersection between all three here. Okay. So these CA systems, they guarantee to give a correct response, but only while the network is working okay. So they can provide consistency and availability so long as there's no partitions in the network, so long as there's no problems between the machines and the communication between the machines. So CP systems, they guarantee that the responses are correct, even if there are network failures, but the response may fail. These are also called weak availability. So in general, if there is a problem with the network and certain nodes cannot communicate, it may fail. It may reject a request. It might say, sorry, right now we have problems. We can't answer. We can't add your data. We can't answer your query. The AP system is different. It will try to provide a best effort response, even in the case of network failures. So it's sort of like it will try its best to give the best possible response it can give right now, even if it's not strictly speaking the same answer that every node or every machine in the distributed system would return, even if it's not necessarily sure to be a consistent response. So here we assume the network always works fine. Here we say, if there's failures in the network, then we'll just, we may reject requests that we can't be sure about. And here it says, we'll try to answer every request, but we might have to reject, we'll try to answer every request, but some of the answers might not be fully up to date, for example. And these are called eventual consistency systems as well. So, okay, in terms of CA systems, let's look at the three different options we have. Essentially, we cannot have any partition. So we can't generate somehow the proof that we saw, no, that counterexample no longer, for Cap is no longer a counterexample. So essentially we can maintain everything, you know, respond to requests and so forth, and maintaining a consistent and available system. The CP system, okay, so we have this partition, and now what we say is, okay, so what are we going to do, right? So we have a request, how many users start with M, and according to C, we cannot give an inconsistent answer or a sort of a best effort answer. We have to be sure about what we return. There is a partition. So what will we do? Well, what we can do is just say, we can't respond to your request right now. Okay, so you know, maybe if you come back later when there isn't a partition, we can give you the correct answer. And this is good, you know, in cases where you really do depend on a correct answer, maybe in a banking sort of situation, for example, or maybe in a hospital where, you know, you can't really give a best effort answer. You have to be sure about, you know, what you're returning. A CP system is a good option. And the AP system then is this idea that when you have the request, somehow the system will try to generate a best effort response, which would be in this case, there's 891 users. This is the kind of this is the best estimate we could give right now, even though we're not considering Madonna because there is a partition in the network. So these are overall the concepts. So in terms of AP systems, there is another name for them called basically available soft state eventual consistency. And this is sort of supposed to be, I guess, a clever acronym because we have acid in relational databases, and base is like the opposite of acid. It's like alkaline, alkalino. Alkalino, is that how you say it in Spanish? But it would be, you know, the opposite of an acid. So yeah, so someone came up with this acronym and decided that it would be clever to say base and to oppose acid. Basically, available means it's almost always up. So somehow the emphasis is on responding to everything, not rejecting requests or users. Soft state refers to this idea of replicated or cached data. So you can have copies of data that are not necessarily the most up to date or not necessarily consistent across all of the system, but they allow for, you know, quickly responding to requests, with the idea that there will be eventual consistency. So that essentially when there is a change, like when we add Madonna to the system, okay, so maybe some cached data that we are returning to users is returning like old counts, not considering the new user. But given enough time, the system is trying to auto-correct itself. It's trying to catch up. So even the replicated cache data will eventually see the new user, like we'll see Madonna and include Madonna in the count. So it's basically this idea that we can tolerate kind of approximate answers to enable scalability and efficiency. So we can kind of trade off consistency for availability and efficiency. So this is essentially equivalent to the AP definition in CAP, this idea of a base system, basically available soft state eventual consistency. Any questions or doubts? All good? Okay, so now that we think about this base system, it might be interesting to think about a real example. So in what way does Twitter act as a base or AP system? So here's maybe an interesting question. What kinds of partitions could we have in Twitter? We already spoke about one type of partition that could cause messages to be delayed or lost. Okay, so we can have all the typical partitions, you know, rack switch failures. We could have, you know, with different types of hardware failures and so forth. But we spoke about one from the kind of application side, which is when we spoke in the first class about Twitter, we mentioned that when a user tweets, that tweet is written into like all of the different lists of, or into all of the timelines of the users following that user. So if I tweet and I have 1,000 followers, then that requires 1,000 writes into the 1,000 different parts of the database with the timelines for the users following me. So this can create a partition, right? So when we spoke about this, we said that, okay, you know, what happens in the case of a user that has millions or tens of millions or hundreds of millions of followers? It can take some time for the messages to be propagated in the system and for the database to actually to update itself. So one option would be to try to create a transaction, like a massive transaction, which essentially, you know, does all 129 million updates or whatever as one operation. But that would be extremely costly, right? We'd have to stop all of Twitter while we're doing all of these writes. So this is not what happens. Rather, what happens is, you know, it keeps accepting reads and writes, even, you know, things that might not be consistent, while it's sort of, you know, doing the millions of writes that it needs to update the timelines. So this creates a sort of an inconsistent state, because we're still kind of serving timelines while we're in the process still of updating the timeline with respect to a given tweet. So some people will see it, some people will not see the tweet. You could even have situations where you could see a retweet of the tweet before you see the original tweet, even though you should have received the original tweet, you know, these sorts of situations. So, so you can, you know, have all these sorts of like inconsistent situations that you could see. This is because essentially these users with massive followers, when they post something, they're creating a massive amount of messages that is effectively creating a sort of a partition. It's essentially, you know, it's delaying or, you know, stopping the messages from being sent fast enough within the system. So this, however, will eventually become consistent. You know, essentially once all the writes are done, or when you go to look at your timeline later, you will see that they are in the correct sequence, and the timeline will be reordered according to the timestamp and made consistent. So essentially, if you were to kind of maybe stop all of the, let's say you were to stop all of the writes to Twitter, everyone stopped tweeting, you know, for a day, or not a day, maybe an hour, then everything would become consistent. You know, but the system is always trying to achieve consistency. It just might be delayed a little bit. So this is essentially an AP style system. The CP style system would be, you know, if you looked for your timeline and there was, you know, some sort of partition, or some very popular user had just tweeted and it wasn't finished updating the database, when you went for your timeline, when you look for your timeline, it would just reject the request. It would say, no, I'm sorry, we can't. We might give you the tweets in the wrong order, so you'll have to come back later. And Twitter would fail. I mean, you couldn't build Twitter with a CP type system. And if things are out of order, it's not a major issue, right? Nobody really cares all that much. So it makes sense in this sort of situation to have an AP system, which is almost, you know, it's in the context of relational databases, it would not be tolerated. It would be seen like as something that's incorrect and something that needs to be fixed, and it's wrong. And, you know, we need to look at the transactions and what's going wrong. But here we tolerate it because it's almost the only solution. There's no way we can have like an ACID type system that, you know, is dealing with this amount of data. Okay, any questions or doubts? Okay, so we'll take a break in a few minutes. Oh, no, we can take a break now. So 3:10. Yeah, so maybe just to briefly finish. So we in general, in distributed systems, partitions will happen, right? We won't be able to send the messages as quickly as we like. So in practice, what we do is we fix P, and then we have to choose some sort of trade-off between C and A. It's not that, you know, these are binary decisions. We can have systems that are more C or more A, or, And we'll see how this can happen in a practical sense a little bit later. So let's take a break until 3:20. Let's see then. Any questions or? It's a good time for me to read up more about latching, so I can answer the first question. Okay, see you in 10 minutes. Recording. So with respect to the latching here, the idea is that a latch is like a lower level lock. So it's essentially at the level of specific indexes. Locking is sort of for transactions, and it would allow you to undo an entire transaction, whereas a latch is like a lower level lock on a specific, for example, index. And it isolates different threads rather than different transactions. So it's like a lower level, it's similar to a lock, but it's a sort of a lower level, thread level lock that prevents two threads from somehow leaving a particular index in an inconsistent state, for example. So it's something particular to implementations. Regarding Cap, so yeah, the point with Cap would be not so much that we have to choose a CP system or a CA system, but typically we'll assume P happens, and then we have to maybe choose some sort of trade-off point if we want something more consistent or we want something more available. So we can see that in practice later. Any questions or doubts? Okay, so in terms of partition tolerance, we have to talk about the different types of faults that can occur. Sorry, let's see if I can chat. No, I've lost the chat. Don't know why this always happens. The two windows are fighting for each other. My presentation is fighting with the chat. Let me see. It's coming up behind my presentation. Now it's completely disappeared. Okay, there it is. Sorry. No, okay, let me try that again. We're going to put chat up. Now we're going to get rid of chat, and then I'm going to share the presentation. Yeah, okay. So sorry about that. So when we talk about partition tolerance, we have to talk about different faults. So we can have problems with the hard drives. They can become melted, or machines can melt, or we can have rodents eating the wires. Maybe someone has installed Windows on one of the machines. The server room can become flooded. Maybe there's some other sorts of natural disasters involved. But oftentimes a lot of faults are actually due to a high amount of traffic that we can't process in a given period of time. It might relate to maybe a network switch that fails. Maybe one machine is down and another is coming online to replace it. So there are different types of faults, yeah, but we can sort of abstract two different types of faults that are key to think about, that allow us to abstract away a lot of those details. So the first is a fail stop fault. And the idea is that a machine in the distributed system fails to respond or times out. So if there's an error, it just does not respond with anything. So often this is due to hardware or load. So, for example, maybe, this is a processing example. It could also be a database example, like how many users do we have that start with M? But we asked two machines for, some results. They return, they aim to return. In parallel, we're asking them to do the same task or to find the same value. One of them fails, the other one returns a correct result, and we're fine, right? So if we think about how many machines we need, where F is the number of failed stop faults, we need at least F plus 1 replicated machines, where the plus 1 So we have F that failed, and we just need one that works. And once we have one that works, it returns the correct response for the lookup, for the task, whatever we want to do, we are fine. We can take that result and we're good. So if we assume that all faults are fail stop faults, we can manage up to F plus one, or we need at least F plus one machines to ensure that we get a correct response. So with F plus one replicated machines, for example, with 3 machines, we can tolerate 2 fail stop faults. If we have 7 machines, we can tolerate 6 fail stop faults. So long as one machine returns the correct response, we're good. So F here again being the number of fail stop failures. There is a different type of fault called the Byzantine fault, which is this idea that a machine can respond incorrectly or maliciously. So it will respond, but it could return the incorrect answer effectively. So this is a more difficult case to resolve, because if we ask 2 machines for whatever task to do some processing to return some value from a database, one fails, but it fails rather with a Byzantine fault rather than a failed stop fault, then we have a problem, right? So we have these 2 different results, and which do we trust? Okay, so in this case, it's not really clear. So essentially, we have a problem if we just have one Byzantine fault with 2 machines. So in general, which one are we going to choose? It's not clear. So if we had a 3rd machine, then we could somehow take that, we could somehow use those 2 responses. So in this case, any ideas how many working machines do we need in the general case to be robust against F Byzantine faults? So if we have F plus 1 clearly isn't enough, right? So somehow what we would need is that the correct responses would be in a majority. So we would need at least 2F plus 1 replicated machines, right? This would be in the case, the very worst cases where all of the faults agree, right? So we have, if we have 5 machines, we can tolerate 2 Byzantine faults, because even in the worst case that the 2 faults return the same results, the same incorrect results, we can still take the majority and be okay, right? So with the algorithm of taking the majority response, we were still fine. But if we have more than that, if we had 3 Byzantine faults with 5 machines, then we're going to have trouble, right? Because we'll take the majority one, which is actually incorrect. So Byzantine faults are actually more difficult to avoid, let's say. So this gives us this notion of distributed consensus. And we can do, an example of this. So there's different types of ways of getting multiple machines or multiple nodes to agree on a value, even if there is some disagreement between the individual nodes. So you've probably seen this dress before. What color is this dress, do you think? What color do you think the dress is? Let's see, maybe we could try a poll. I've never actually done this before. No, what's it doing? It's opening. Why is it? Okay. Add a poll. Color of dress. It opens up the web to do this. Type your question here. What color is the dress? I've never done a poll on is the dress on Zoom. Multiple choice, single choice. So what we got: white and gold, blue and black. Black. What was the other one? Was there another one? Gold and white, white and yellow. Yeah, okay. I think there was sometimes a 3rd option. Save. Okay. So you should have a poll now. I just wanted to try it. Wow. White and gold. Okay, so what we have here is a distributed system in the sense that, you know, you could be different nodes of a distributed system. And now we have this question of what is the actual value that we take? Is there a consistent value that we can take? Can we agree that there's a consensus or not? How do we define a consensus? And what, you know, what value do we take, if any? Maybe we reject and we say, actually, you know, in a CP system, we say our nodes cannot agree, right? In this case, we have 14 for white and gold. They're incorrect. The address is blue and black. But anyways, so our distributed system, usually it's actually the other way. Usually blue and black is the most common response. But yeah, okay, so do we have consensus? Right, so there's different definitions of consensus. What do we actually mean by consensus here? So we got 58% for white and gold and 42% for blue and black. Okay, so in terms of distributed consensus, there is the notion of strong consensus, where we say that all nodes in the distributed system need to agree. And in this case, we fail, right? So in the case of the dress, we obviously don't have strong consensus. We have some disagreement on what color the dress is. So in this case, we fail. We have to say that, okay, sorry, error, we don't know. There's a problem in the system. So we would only have that if all the nodes agree. Okay, so in this case, there's consensus. If we are applying strong consensus and we find that one of the nodes says white, then there's no consensus. Okay. So again, we don't actually have an external notion of truth here. It's just we have to look at the responses and decide whether or not there is consensus. Which is to say that if all of the nodes said white, there would be consensus. Okay, so another common option is to have a majority consensus, where we need a majority of nodes to agree. So in this case, we need 3 nodes because we have 5 nodes in total. We need 3 nodes to agree. So in this case, we have consensus, and the consensus is blue. Okay, so we'll accept the value blue from the distributed system. In this case, if we have 3 that say white, then we say there is consensus, and white is the value chosen by the distributed system. If we have a split like this, 2, 2, and 1, then we say that there's no consensus. No value can be chosen. We need to rerun the process. We need to reject the request, whatever needs to happen then, but we can't agree on the distributed system cannot agree on a value right now. And we can have a plurality consensus. So this is where a plurality of nodes need to agree, which is essentially there needs to be the option with the most popular option needs to be unique, right? So in this case, we see blue is uniquely the most popular option because it has 2 and no other option has 2 votes. So there is consensus, and the consensus is blue. In this case, we have 2 for white, 2 for blue, and 1 for green. So in this case, we say that there's no consensus. There's no plurality here. Another option is to specify, this one is actually quite common, is to specify a number of nodes that need to witness or agree on a value. So in this case, we would say n nodes need to agree. So if we have, n equals 3, for example, then we have consensus. If we were to say n equals 4, we wouldn't have consensus, right? So n equals 3 consensus because we have blue 3, n equals 4, no consensus. So one of the benefits of consensus with n equals 3 is if we ask the machines, maybe we start here and go here. Once we find 3 machines that confirm, we can stop. We don't actually need to ask all of the machines. Okay, so we just need to ask, many times we'll just have to ask n machines. And if they give us the same answer, we're done. If not, we may have to continue through the rest of the machines to see if we reach this level or not. So actually the order in which we ask the machines could also affect the consensus. So if we ask for n equals 2, in this case, for example, the first 2 machines will be asked. So we could end up with a consensus on blue, and we could end up with a consensus on white. It just depends on what order we ask the machines, but we would stop once we find 2 machines that confirm that value. So there would be consensus, but actually it's sort of non-deterministic in this case, depending on which machines we ask. Okay, So what would be the value of n needed to ensure a deterministic or unique consensus with n nodes? How many nodes would we need to ask? So for 5, if we have 5 nodes and we wanted to use a quorum of n, how many, what would we have to define n to be to ensure that we can never have this sort of situation of a non-deterministic consensus where it could be blue or white depending on which order we ask the machines? So if we think about it, 2 is obviously not enough. Would 3 be enough? Could we have 3 machines giving, could we have 2 different options with 3 votes, let's say, from each machine? We can't, because that would be greater than the number of machines there. So we can choose n to be greater than the average, right? So in the case of 5, it would be 3. In the case of 6, 4, 7, 4, 8, 5, and so forth. Okay, so we need n to be greater than than half the machines. We need a majority effectively. Okay, so in this case, if we want to have a unique consensus, we would use the majority consensus rule. Another option is consensus off, which is like a quorum of 1. Yeah, we just take, if a machine gives us an answer, we trust it, and we go with that. So in this case, we'll just take whatever value. We just ask one machine and take that value. We assume it's correct. So in this case, there's consensus on, and the consensus could be on one of 4 different values. So here we have different options with different levels of strength or weakness. So strong consensus, majority, plurality, quorum, consensus off. Of course, quorum is variable, so it's sort of not strictly correct to align it like this, but in general, quorum will be something like 2 or 3 nodes. So it'll be less than the plurality, majority, or strong consensus. So keeping that in mind, we have a sort of ordering of consensus where, okay, quorum consensus doesn't really fit into the total ordering. So which of these kind of extremes seems more CP and which seems more AP? So CP is consistency again. So which option would you think offers more consistency? CP or AP? Or is which type of consensus? Yeah, so the strong consensus kind of end here of the spectrum is CP, and the consensus off end of the spectrum is more AP. So we can think about it in this direction, because if we have a strong consensus, we have to say, no, we don't know what this value is, and that's essentially like an error. It's like, we don't know, sorry, you asked us something, but there's an error in the system right now. So this kind of tends towards CP, which is being more strict in what values we accept and return, giving a more consistent answer. And this is more AP in terms of returning responses to more requests. So in terms of scale, which would be more scalable? Consensus off or strong consensus? So yeah, probably you would guess here that strong consensus, we have more replication, we have more messages, we need to ask more machines at every stage. So this has a higher cost and therefore less scalability. And here we can just ask many machines potentially. In general, we probably also need less replication. So in general, we can say that consensus off is the most scalable option, or easier to, has the less cost, has the lesser cost, and is easier to scale. So which is better? There's no which is better, which is worse. It's a trade-off, right? And the choice is often application dependent. In fact, many NoSQL stores will allow you to configure the level of consensus, the level of replication, and this allows you to kind of have some sort of, trade-off, to find the point of trade-off you want between a CP and an AP system, right? So whether you prioritize more availability, or you really want the answers always to be correct in terms of a CP system. Any questions or doubts? Okay. So we have different types of NoSQL stores. So we've talked about kind of Cap and some general ideas of distributed consensus. These underlie almost all distributed NoSQL stores. Um, Now we'll talk about the flavors. So the first flavor is the key value stores of NoSQL. So these guys here, which are the simplest but the most scalable. What are they? In a word, they're a map or a dictionary, right? Or an associated array. So essentially you have keys and you have values, and you have your very typical kind of interface, which is your put key value, your get key, which will return the value associated with that key, delete key, which will just remove the key and the value. And that's pretty much it. Sorry. So yeah, that's key value stores. um, so the cool thing is that they're distributed, right? And they can be potentially massive and distributed over many, many machines. You can do also a lot with the map. You know, your values can be not just simple values, but you could also think about, you know, encoding, you know, almost like documents, or having some list of values with keys and values, whatever. So you can, you know, use a simple abstraction to on a lower level encode complex values, for example. So here we have also keys, you know, which we may try to think of coding coding different information into keys, but in particular, it's more useful encoding, you know, the values, lots of different attributes and values associated, for example, with a given key. So yeah, given a key, we'll get back a value. So in general, you could, you know, think about modeling any sort of data in a map. The thing is, it's just even in a relational database, for example, if you think about it, when you're looking at the indexes, you know, you have a key, which is your index column or your primary key, and your value will be the entire tuple. So this is almost like just a lower level data structure that you would use for optimizing relational databases as well. You can model pretty much any data in a map, but it's not necessarily the case that the data will be in a normalized form or that it will be free of redundancy, right? But it's still sufficient for many applications to have something like a map. So if we think about, you know, what sorts of use cases, why is this sufficient? Why are we getting rid of relational databases for key value stores? We can look at the sort of origin of key value stores. And one of the seminal key value stores, DynamoDB, was proposed by Amazon. So in Amazon, okay, online store, you can go, you can buy different products. Amazon is a large company, has other different aspects as well. But on the main online store, we can, you know, buy different products, and it has information about the prices, detailed stock, and so forth. So also it has to manage some information about clients, about customers, shopping carts, accounts, and so forth. So some customer information, and maybe also some data for recommendations to be able to, you know, compute recommendations from these customers who bought these items also often bought this other item, for example. So they had a huge, you know, a very large growth in clients and customers through the years. And they started using, you know, relational databases at the start to manage the data that they needed. And they started, you know, storing the databases across different machines and trying to distribute them and so forth. Also, you know, aside from the online store, Amazon also has, you know, web services, has all sorts of different AWS, right? So it has all this different types of services it provides. And, you know, they also had some pressing requirements for data in those scenarios as well. So anyways, with all of this growth, the databases were struggling with the data that, you know, were coming in. So essentially what they realized was that kind of using relational databases with ACID and SQL was kind of overkill. It was more than what they needed. They weren't using most of what SQL and ACID had to offer. What they found is, you know, a simple map is often enough. And that they didn't really have, you know, in some cases, need for transactions or strong consistency. For example, in the case of recommendations, it's not, you know, the data don't need to be strong, you know, very, we don't need to guarantee consistency in those cases. You know, some recommendations are good enough. So in terms of a simple map, for example, if they have a product, you know, if you have a product ID and you want to show on your web page all the information for that product, really all you need is a key value, a map, right? So you give the product ID and you get back all the metadata information about that product that you need to create the web page to display on the web page. So it's not really that you need to, because your queries are so repetitive, you can just sort of you can pre-compute them into keys and values. So given a key, which is a product, you get back all the information you need, right? So they decided, okay, let's just simplify all of this. Let's get something that's easier to distribute, more scalable, more simple, but turns off a lot of the features we don't need. And this was the key value store, which is Amazon Dynamo. So this was proposed around 2007. So this was an initial key value store, and this was sort of when they were starting to really face this increase in scale and wanted to look for more efficient solutions, custom solutions. So the goals would be scalability, ability to grow horizontally, in other words, add more machines to handle more data, high availability. So you wanted, sort of an AP type system that, you're not rejecting any requests because that will lose you money. Performance should be fast. And what can you do to achieve these goals? You have to trade something, right? It's not like you can just magically have all of these things and ACID and SQL and, do all of this on a Raspberry Pi, right? What you're going to trade is that, okay, you're going to need lots of machines. You don't need full SQL. So you're going to give away the query language and say, I don't need this anymore. And you're going to give away ACID. So you're going to give away transaction support. With this, then you can start to think about achieving these goals. Okay, so in terms of distribution, how might we distribute a key value store over multiple machines? Well, the probably obvious idea would be to, like in MapReduce, apply the mod hash key m function, which you take the hash of the key, you do modulo m, which is the number of machines, and that gives you an ID of the machine on which you can index, right? So this is pretty straightforward, a pretty straightforward option. There is a difference though compared to MapReduce or Spark, which is that we're going to be storing these data kind of persistently over time. It's not just we're going to distribute them for some task, compute the result, and save the output to HDFS. In this case, we're going to be storing these data over time. So what happens if we've already created our index with 4 machines and now we add a 5th machine, right? What happens if a machine leaves or joins afterwards? So that would change the number here from 4 to 5 or 4 to 3. And now all of the locations of all of the keys that we've chosen so far, we've lost that, right? So now it's sort of like we've shuffled everything. So every time we add a machine, it would be like we'd have to rehash the entire data set, which would be a complete nightmare, right? We want some flexible scaling. So can we avoid rehashing everything is the question. And the answer is that there is a solution to avoid rehashing everything, which is called consistent hashing. And the goal is, when we add a machine or remove a machine, we don't want to have to rehash everything. And the idea is to hash using a ring. So we're still using hashes, but instead of defining it kind of as a numeric value, we define ranges. And these ranges form a ring. So we have an example here of a ring, and the hash might range from 0 to 1, let's say, or 0 to 2 billion. It doesn't really matter, but essentially we assume that it loops back in itself. So that here, you go from 0 to 2 billion and then back to 0 again. So each machine then picks n pseudorandom points on the ring. So these colors here are different machines, different nodes in the distributed system. And these machines, essentially on the ring, they define an arc that they control by choosing random points on the ring. And then they will take control of the points before that arc, right? So they pick a point, and then whatever kind of range there is between this and the previous point on the ring, that's their control. They own that arc of the ring. So each machine is then responsible for the arc beyond its point. Okay, so then we hash objects. We hash, for example, keys into this ring. So we create a hash for the object and then we map it to the ring. And that tells us which machine is responsible for that object. Okay, so And that's it. So the nice thing now is that if a machine leaves, rather than having to rehash everything, we just have to move it to another machine. So if a machine leaves, okay, we need to move all of the objects from the red machines, but we can just move them, you know, all these to the green machine, for example, all these red ones to the blue machine, all these red ones to the green machine. We can move them to the adjacent machine in the ring. So we only need to move them from the adjacent from the machine that's leaving. Of course, if the machine leaves, we can't move anything, but we'll talk a little bit more about that. We can move them from a replicated machine. So we'll talk about replication in a little bit. If a machine joins, it picks new points. So it somehow picks points in this ring, and then the objects are assigned from the machines that were originally indexing them. So in general, the main benefit is that we only, if a machine leaves or joins, we only have to move the relevant data for that. We don't need to rehash everything. Okay, so we only need to move the points that are really necessary. And Amazon Dynamo uses this consistent hashing scheme based on 128-bit MD5 hashes, right? But essentially, what's most important is this concept of consistent hashing. So if you add a machine or remove a machine, you don't need to rehash everything, which is pretty sweet. So, you know, in Dynamo, we can also have replication factor. So we can set a replication factor, for example, of 3. If we have a replication factor of 3, then we keep 3 copies of everything, right? And so here we have 3 copies of the blue stuff, and we have 3 copies of the orange stuff. So what we'll often do is to define here a primary replica, which are the darker colored ones, which are the ones that that control the reads and writes to that chunk of the data. So how do we implement replication factor in terms of consistent hashing? It's relatively simple. So instead of just assigning an object to you know, the current arc of the machine, we can also move to the next arc and the next arc, depending on the replication factor. So we just kind of go along the ring and pick the next, you know, n-1. We pick enough machines in the order of the ring to satisfy the replication factor. And that's it. So consistent hashing is an elegant solution to this problem to avoid rehashing everything. Okay, any questions or doubts? Okay, so in the Dynamo model, we have what's called a named table, which has a primary key and a value, and the primary key is hashed or unordered. So the distribution is by hash, as we saw. So this means we can't do ranges on the keys. So we essentially get back a very typical map structure where we can look up a key and get its value. And the value can be potentially complex, right? So you can encode some bunch of data. So this is the overall structure. We can have different tables. So we can have, you know, different maps, essentially one for countries, one for cities, and so forth, one for products, one for recommendations, one for users, whatever we need it for. In terms of CAP, we have 2 options for each table again. So we can have a CP system, which would be, or an AP system first, sorry, which would be this idea of, you know, emphasizing availability over consistency. And we have a CP system, which is emphasizing consistency over availability. In terms of consistency and how it can be implemented specifically in a NoSQL or distributed system, we have the notion of a vector clock. We have two or three different techniques that we can use to make sure we have consistency. So the first is a vector clock, and the vector clock is a list of pairs indicating a node, a server or a machine in the distributed system, and an operation count, how many times that machine is operated on that object. And this can be used to track branches of revisions. So what we have here is essentially, we'll assume that there is like this object D, this data object D, okay? And we have the first version of D here, which is written by the server X, machine X writes D. So we say server X has operated on D 1 time. then we say, okay, in the second version, let's say X updates D, right? So, D could be, let's say D is a shopping cart, right? So the shopping cart's originally created by server X. Then maybe server X takes care of adding another item to the shopping cart to create second version of D, of the shopping cart. And it increments its own counter to say that 2 operations have been done by server X on this. Now, maybe for whatever reason, we might have 2 parallel, modifications to the shopping cart. So we create a D3 here and a D4. Okay, so we have 2 different versions. And here we have essentially one is handled by server Y and the other is handled by server Z. So in this version here, Y will keep a counter here to say that Y has operated on this once, and here we'll have rather a counter for Z to say that Z has operated on this once. Now, if we look at the 2 vector clocks, which is just this kind of pairs of how many times each server has updated this shopping cart, we see that somehow they must be parallel versions because Y has done something here and Z has done something here and they're not contained within each other. So we know that we have 2 parallel versions that have to be merged and reconciled and handled. So these can be reconciled and written by one server. Let's say they're reconciled or merged by server X again. In this case, this counts as an operation. We can say that now server X has applied 3 operations to the shopping cart, server Y 1 operation, server Z another operation. So this vector clock idea is used to indicate essentially how many operations each server has applied to a given object, to a given object of interest. And that allows us to know when we have divergent versions of some object. So the question then is how to do the reconciliation. So if we end up with 2 versions of one shopping cart, right? One with these 2 products and one with these 2 products, these are supposed to be the same, but somehow, in the distributed system, we've ended up with diverging versions. How should we reconcile them, right? So should we take the intersection, like just leave the one thing that's in common? Should we take the union? Like, should we, somehow take the 3 elements we see in both? So there's no clear answer to this. So in terms of how best to merge the multiple conflicting values, known as reconciliation, this is something that must be, defined. Must be defined at the application level. We have to say how reconciliation can be done. So in terms of consistency, there's also the question of, how we can compare 2 different very large maps, 2 very large files in general. So, and if we compare them, how we could see if they're the same or different, and if they are different, to find out in what part of the file they're different. So we can have very large tables or maps like this, two different versions that are supposed to be replicas of each other, copies. And to ensure consistency, we'd like to make sure that they're the same. And if not, identify where they are different. So one technical solution to this is to use a Merkle tree, which creates a hash tree over here. We have our data underneath here, and then we create hashes of the different blocks of data in sequence. And then we create hashes of the neighboring hashes. And then we create hashes of the neighboring hashes. And until at our root node, we have a hash of the entire data. Okay. And then if we have 2 different copies of data and we have 2 Merkle trees, we can compare their root to see if all of the data are the same or not. Okay. And if they're not the same, then we can check to see the left child or the right child to see if they differ. And if one of them differs, then we know that that part of the file must be different. And we can use this to do a sort of navigate the tree to find exactly in what region of the file or what regions there are differences between 2 different versions. So these are just some techniques to give you an idea of how consistency can be implemented in practice in a physical system. So you can read more in the white paper if you're interested in that. So there's a few more minutes left, so I won't be able to finish. Oh, they just shut off. So let's, I'm out of time as well. So let's end the class, but I think there isn't so much more left. Any questions or doubts? No doubts. So hopefully I wasn't going too quickly over those elements. So there's some things I also, if you want to look at the PowerPoint, there's some other details about versioning in Amazon DynamoDB and so forth that you could also check out, but I don't think they're so essential. So on Wednesday, we'll talk about, we're going to play with Cassandra, which was originally a key value store and later became a big table or wide table store. So we'll talk a little bit about that before to finish the class, and then we'll play with Cassandra. So it's like a very simple relational database where you can't do anything. All you can do is very simple queries. So the kind of difficult thing or the interesting thing is the partitioning, how the data are partitioned across different machines, what kinds of queries you can do. And depending on how you define the partitions and keys, you can do different types of queries or not. So that would be the subject for Wednesday. Any questions or doubts? Okay. If not, see you on Wednesday. And for those who saw the dresses being white and gold, I'm not sure what to tell them. It's a question of the light. Your brain is playing tricks on you. See you on Wednesday.